Okay, welcome everyone. It is a pleasure to introduce a great friend and a colleague today, Kostas Bekris. I've been fortunate to know him for many years. I know his advisor well, Lydia Kavraki. He is he went to undergrad in Greece, the University of Crete, and then moved to Rutgers. Then moved to Rice, where he worked with Lydia on his dissertation, which is in motion planning. And then he spent a little time at the University of Reno, or University of Nevada in Reno, building up the robotics program there, then moved to Rutgers, where he is today. And he also has an appointment at Amazon. And so his part-time position there is doing research with the Amazon team. And his research, I've always admired him because he works at this intersection of motion planning and practical applications. So he integrates sensors, he integrates a deep understanding of the physics and mechanics of manipulation with manipulation and grasping. So he's also been very interested in recent years in simulation. We ran a workshop at RSS on Sim2Real, and we had some really fun discussions about that. I'm really excited that he's here. I should mention also that I had the great pleasure to work with him when he and Peter Nabil and I ran the Wafer conference in San Francisco in 2016. So he's a great person. I'm really excited that he's here. And please join me in welcoming Kostas. Kostas.
Great, thanks, Kane, for the kind introduction. So today I'm going to be focusing on two themes that I think are important for us to address to achieve progress in robotics. And I think all of us are excited for making this tradition in the field from the traditional success story of robotics in high volume manufacturing to some of the exciting applications, putting robots out in the field or perhaps into homes. So field robotics, service robotics. But I think where we are today in terms of applications, we're somewhere in between the highly structured setup of manufacturing to the completely unstructured setup. And I see autonomous driving as a stepping stone towards field robotics, and I see logistics as an important stepping stone for service robotics. I'm joking sometimes that, if e-commerce had not been discovered, perhaps roboticists should have discovered it to make progress with robotics. Because it is a setup where we can have a little bit of structure. We know perhaps, the general location of where objects can appear, but at the same time, relative to manufacturing, we have a much larger variety of objects that can appear. So this allows us to get access to data, that to train methods that allow us to eventually get perhaps into the home where we have to deal with highly, more deformable objects like food and other more challenging setups. So in this transition, we want to also achieve different new objectives and go from the very fast, accurate, very repetitive robots of the past to robots that are much more adaptive, versatile, robust, and safe. So I'm coming from the computer science side. So the question is, how do we put together robotics AI systems to address these challenges? And I'm going to use the domain of logistics first as the application domain for solving such problems. So I'll go back in time in my academic career and go back in 2015, where Amazon announced their picking challenge. So we were tasked, academic teams to pick objects from a shelf. So we had to detect that object and be able then to pick it up and drop it into a bin. So, we had a limited amount of time, so we tried to put a system that was executing, rather a textbook architecture: sense, plan, act. We were first reasoning about the order of objects to pick, then the perception was responsible for detecting objects, estimating their 60 object pose, and then we planned towards specific grasps and collision-free object motions to do pick and place, and then we executed that. I think this is a very popular pipeline, and one can ask what could go wrong, in the Amazon picking challenge with this sense plan architecture. Well, everything can go wrong, right? Your sensing is going to have noise, maybe erroneous. Your planning may not discover solutions even when they exist, given computational limitations. Your execution may be erroneous, and this is where we have this emergence of this gap between perception and planning, and how the communities have kind of developed solutions independently, not necessarily thinking of the integration in the context of robotics. As a motion planning person, very frequently we assume that perception has solved all of the problems in terms of providing us an accurate representation. There's of course a lot of work on planning under uncertainty, but even this belief-based planning often makes convenient assumptions about how perception fails. We say, okay, I may not know perfectly the object location, so perhaps I'll throw a Gaussian distribution around the estimation, and then I'm going to be able to reason about robust plans. But this is not how perception fails, right? You may not be able to see at all an object that exists, or you may see phantom objects that actually do not exist in the environment. So I think it's much more important to think about tighter closed loop operation between planning and perception, and also think about what are the appropriate common representations between these two domains that perhaps will not require too much effort and data to compute on the planning, on the perception side, but they're going to be informative enough also for fast planning. And another aspect here as well that is important is the actual mechanisms that we use in order to solve these problems in the form of the end effectors, perhaps, that we're deploying. In the original Amazon picking challenge, we had the rigid end effector. The actual environment also was metallic. Any failure would result to injuries in graduate students and damages. And the presence of compliance is something that we should also try to take advantage in this process in order to help us with safety and adaptability. And a big part of the community is focusing actually on this, mechanical intelligence and how robotic mechanisms can actually help us solve a lot of these problems. And I'm a big fan of the development in the field where we're also transitioning towards softer robots. For instance, we collaborate a lot with Aaron Dollar's group at Yale, and he has been building adaptive hands. They're under-actuated. So in some sense, in that case, the hardware helps you a little bit not to have to perceive and plan everything perfectly. The hand adapts naturally to the shape of objects and to sensing noise. At the same time, especially for this emergent domain of soft robots, this is where some of our traditional modeling tools are having some of the bigger challenges. These are the types of robots that are more difficult to precisely model and accurately predict what will be the effect of their actions. So some of the traditional analytical tools for control are much more difficult to apply, which motivates the use of some data-driven solutions. For instance, you may want to use reinforcement learning for control. But even in this case, if you're going to go in developing a data-driven solution for control, now data requirements becomes a question. You may have to collect a lot of experimental data with your robot in order to train the RL-based controller. So again, you would benefit from the presence of a model, of a simulated model, to train the solution first in simulation, so as to reduce the need for a lot of experimentation with a physical platform, which is quite cumbersome and it requires manual effort. So this other gap that is important is that we will always need models in the end, even if we're going to use analytical methods or data-driven methods, and we have to see how we can reduce the difference between those simulated models and how the robot behaves in the real world. So I'll try to get into how we are trying to approach these two gaps, and I first will focus on the gap between perception and planning, especially in the context of robot manipulation. And I'm going to assume in this discussion that our sensing information that we have available comes in the forms of RGBD data. I'm not going to get into tactile information. Our work has been primarily on vision-driven manipulation. And we'll try as well to use compliance as much as possible in a lot of the efforts that I'm going to be describing here. So let's get into another case study of a manipulation challenge that we worked on. Before I described this traditional sense plan act implementation for the Amazon picking challenge, let me talk to you about a packing project that we worked on a few years later, back in 2019. our challenge was to pack objects that appear originally on a bin in an unstructured pile. For instance, you could have this toothpaste and this soaps, and you want to tightly pack them into a new bin, and you have to transfer them. And we assumed that what we had access to was a minimalistic end effector, just a suction-based end effector, and we had a 7 degree of freedom Puka arm, 2 RGBD sensors, one focused on the picking scene and one focused on the placing. And the first thing that we did, we went ahead and did the baseline approach. We would sense to detect the objects in the original bin. We would pick them and then place them into the target bin. And what can go wrong? Again, every step of this process can go wrong. And now you have to think about the feedback loops that you need to introduce here so as to make the solution robust. So the actual pipeline that we ended up implementing just to solve this problem had a lot of those feedback loops where, what if you try to pick the object in the initial unstructured pile and the pick failed? What if the transfer failed? You have to resense and reevaluate what happens in the environment. And we had to develop in the end adaptive behaviors that would actually allow us to solve the problem effectively. So let me focus into specifically 3 behaviors that are allowed to deal with failures. One is to topple the object in the original bin, to adaptively place it and push it into the place scene, and also perform corrections during the final placement. So what can go wrong in the pick scene is that you may try to pick a specific object. Let's think about these cuboid soaps. And you want, let's say, to place them in their large support surface. But what has actually been exposed in the pick scene is another surface. And you are using this simplistic end effector, the suction cup, which does not provide within-hand manipulation capabilities. So how can you reorient the object so as to expose the surface that you would like to pick from, so as to place it with a desired orientation in the place scene? Although you have a minimalistic end effector, you can still do some form of reorientation by taking advantage of the environment. For instance, you can try to figure out locations inside the pick region where you can place the object and then topple it, use actually the suction gripper as a finger to drop the object and expose the desired surface, from where now you can apply the suction cup and place it into your target region. Now, when you go to place it into the place bin, you may think, okay, I want to place it exactly where I want it to appear. But perhaps that you already have failures in the scene where the objects exist, and you need to reason whether by trying to directly place it where you believe it should appear will actually make things worse. So actually, instead of doing this, we perform what we call adaptive pushing. We try to sense the scene and figure out, given the point cloud of the region where the object is supposed to be placed, whether undesirable collisions might arise. And we define a retract vector where we're not placing the object directly where we want it to end up, but we try to figure out a location that is collision-free relative to the existing geometry, and then push towards the desired location. And this pushing also has the effect that it kind of packs the objects that are already there. So we place it somewhere that actually minimizes collisions and then adaptively push towards the target location. Finally, you may even have these failures where you place an object, but actually now it stands on top of some additional, some of the existing objects in the scene. Your suction cup can still be used as a finger. You can drop objects to align them in the same surface, and then you can also pull them up in order to tightly pack them. So again, you have to have these operations that you're reasoning about all of the failures so as to be able to address your problem reliably. And we did a series of experiments here in an ablation study for how things look like at the end At the bottom, we see what happens if you just do the standard sense, pick, and place operation without these adaptive behaviors. You see that you end up with you're supposed to do packing, right? And the target bin looks as unstructured as the initial bin. And then we started introducing incrementally these behaviors. So if you perform toppling in the initial bin and your corrective actions at the place scene, but you do not adaptively push, then you may not be able to place all of the items. Actually, the second row from the bottom corresponds to not actually performing toppling in the pick scene. If you don't do adaptive pushing in the place scene, you're seeing that again the objects are quite in a structured configuration. Without corrective pulling, at the end, there may be a lot of gaps between the objects. But only once you have all of the behaviors described, we were able to reliably execute successful packing. So that's an example of how your high-level task planning process can actually introduce corrective primitives that adapt to failure, and we could then solve problems as I showed before, where we can have heterogeneous a set of objects. We perform pose estimation as well in the target bin to figure out what is a good pick location, and incrementally remove objects and pack them. We were able here to figure out which ones are toothpaste from the soaps, and separate them and do two separate packing. So I'll jump a little bit forward here. You're seeing actually the placement of the soaps, and actually the soaps here it's a situation where we can pick it from its stable surface, and we have to actually raise it to its less stable support surface, and actually compliance at the surface of the bin of the initial bin helps with that. And then we can apply suction in order to place it into the target bin at the desired configuration.
Kostas, can I ask a question on this?
Sure.
How do you know, and maybe the answer is you don't, but how do you know ahead of time that the three kind of adaptive actions that you have proposed will allow you to will solve the issues that you've observed? Is there a way to, do you think, in thinking about this, to kind of geometrically capture the issues and then say, aha, I really need kind of these three corrective actions, and with that I think I can span the space of corrections that I need to get the packing result that I want?
Yeah, so here we kind of manually define the behaviors by experimentation and figuring out failure modes, and then realizing that how we need to address them. But you're right, it's a very important thing to kind of being able to verify some conditions, so that if you have a target specification for what needs to be achieved, that you can kind of verifiably get to that given all the failure modes. We have some line of work on trying to figure out the conditions under which a behavior is going to succeed in given a specification, not mature enough to be, however, deployed in a kind of a complete manipulation pipeline. So here we had to kind of come up manually with these behaviors.
Thank you.
And the focus of this work was mostly on the high-level planning and how to make it robust. But what about the perception side of things? How can we make perception much more informative for manipulation pipelines? And you can think situations, and I'm showing an example here on the top right, where you may be able to have to track the object's pose as it is being manipulated. Here we have a situation where perhaps we need to place an object in a tight area. The object, as it is being picked either by the suction cup or by the gripper, it moves relative to the end effector, and you have to know what is its pose in order to place it into the target region. And we started moving more towards perception solutions that are not just generating a single snapshot of the world and then statically react to it as we were doing during the Amazon picking challenge, but we want perception that kind of actually streams continuously information about where the objects are inside the environment, so that your high level now reasoning to be able to adapt to failures because you have the updated information by performing continuous pose tracking for the objects. And so far we have primarily been limiting ourselves to rigid body pose tracking, and we're reasoning about the 6D pose of the rigid body, so the 3D position and the 3D orientation. And performing 6D pose tracking is challenging because you cannot easily get labels in the real world. So we try to solve this problem by generating only synthetic data, and we are training in a supervised manner a network. We're referring to it SC3 TrackNet, which is responsible between 2 consecutive frames of a video to inform us how much the object that we are manipulating has moved relative to the previous frame. So let's say that at frame T-1 here on the top left, we have received RGB data. We have solved the pose estimation problem at the previous frame. What we are doing then is we're actually generating a synthetic view of how the object should look like given the pose that we evaluated at the previous step in terms of its depth and its RGB image. Then we are getting the latest depth and RGB image from the latest step. And given the difference between where we hallucinated where the object should be according to our previous pose and where we see the object right now in the latest frame, we're trying to figure out the difference in the pose, which can then be added to a previous pose estimate and generate a new solution for where the object should be located. Now, why do we do this where given our previous pose estimate, we're generating a synthetic input to use during online inference and compare versus the real world observation? The reason is that because during training we're trying to use only synthetic data to train this network. During training, we're using synthetic image from the previous step and synthetic image from the current step in order to figure out the difference in the object's pose. When we're transitioning into the real world, we want to keep the input of the network as similar to training and not to have too much of a distribution shift, so that we can have this transfer from simulation to reality, right? And here, one input always remains synthetic, given during online inference, and only the current view corresponds to the real image. And the training happens exclusively in simulation. We go into our physics engine and we generate object poses, the object moves. We are using Blender to generate photorealistic images. We throw all of the machinery of domain randomization in order to assist with generalization. And we have this solution now that gets trained in simulation, and we use it directly on real objects. And together with implementation on CUDA and efficient implementation, we were able to achieve both very high accuracy and very high frequency. In the graphs that we show here, on the x-axis is the frame per second the different methods are able to be executed. So you want to be as far as possible to the right of the x-axis, and on the left, on the vertical axis, we have the accuracy of the pose tracking process. Basically, the difference with the ground truth pose, and you want to be as high as possible. So you want to be on these graphs on the top right. So the proposed SC3 TrackNet actually runs at something like 90 Hertz, which is much faster than what most cameras are actually running, and has achieved very high accuracy as well in the typical benchmarks in this domain. And as you see on the video on the right, even in situations where you can have significant occlusions, the approach is able to recover. And when you see again an object such as this tomato soup in this image, you are actually able to generate a pose estimate given this object model. So with this SC3 TrackNet approach, we use it as an unblocking mechanism to start solving even harder now manipulation problems than the packing example that I showed before, which only performed estimation at specific points in time. So in collaboration with the yes.
Quick question: if you go back, I was just curious about the domain randomization that you mentioned. You showed on the slide before that. Yes, here on the lower left.
Yeah.
So you said physically plausible domain randomization. Can you say a little more about that versus generic domain randomization?
Yeah, so actually, I think when we started doing post-estimation work a few years ago, the biggest gap was actually on the photorealism and the textures. I think, you know, Blender and other tools have become, and NVIDIA's tools have become very good at actually closing the gaps in terms of generating good textures. Where we have a lot of issues is if we train with objects that appear during training in physically unrealistic configurations in terms of their geometry. Objects that, you know, they're not resting stably, they're not they're penetrating one to another. So we make sure that we're actually running physics as well during the training process. And when we have objects in clutter, that we kind of let them rest and then kind of train with the physical constraints into account. And that's where most of the gap actually ends up. We end up seeing that if you are training in scenes that have very significant shift in terms of the configuration of the objects that you see in training versus at testing time, that's where you may have issues with transferring the solution.
Okay. Okay. So the examples on the bottom are for dramatic changes in texture, but not changes in sort of stability of the pose.
Yeah, we try to have the objects, you know, rather unstable, non-penetrating configurations resting stably.
Okay. Thanks.
So we use this tracking solution for a manipulation problem with very low tolerances. So for, you know, these are, you know, peg in a hole kind of challenges where the peg may be only 0.2 millimeters smaller than the opening of the hole that you want to insert it. And what happens in this domain is that, you know, as you're trying to insert the peg in the hole, you're going to have a lot of contacts. As the object touches the periphery of the opening that you want to insert, and every time that you have the contact, the object moves relative to your gripper, and we're using adaptive hands, which help us again with compliance, not to have to be too accurate in terms of our control and sensing, but also allows the object to move relative to the end effector. So tracking is very important in this setup to figure out exactly where the object is located during those contacts. And we're running, you know, this you know, visual tracking that I described before. So we're streaming 6D object poses continuously into a manipulation, planning, and control pipeline that reasons about a sequence at a high level, a sequence of operations that need to be performed. Your object kind of has to touch the opening of the hole, it has to be reoriented and then inserted. And it reasons on how to kind of move the fingers so as to achieve desired changes in the SE3 pose of the object, so that this is going to be achieved. So this integration of high fidelity visual tracking with you know, manipulation, planning, and control allows now to solve some of these classical peg in a hole problems in the wild. And again, this is very low tolerance, you know, 0.2 millimeters to 0.5 millimeters tolerance for different types of objects. The actual manipulation, planning, and control pipeline doesn't reason specifically about the object geometry. It figures what are the changes in SE3 pose that it needs to achieve given what the tracker returns, and then performs the actions for how the fingers need to be manipulated. And this pipeline has a lot of elements, you know, has compliance, has visual tracking at relatively high frequency, and it also kind of closed loop operation between the planning and the perception. So we wanted to evaluate which component of the pipeline matters the most. So we did this ablation where, you know, for we run the whole pipeline for different types of objects, and we tried to execute a lot of experiments and measured, you know, whether within a certain point in time we were able to successfully place the peg in the hole. And you can see the successes on the left side, right? So we ran 12 experiments per object, and we were in the range of 9 to 11 experiments that worked. Now on the right-hand side, we started removing each of the components that we believe helped the system. What if we removed compliance? We removed compliance from the hand, compliance from the arm, and we removed compliance even from the environment. As we reduced compliance in the mechanism, but we kept everything else on the software side the same, we saw this decrease in success rate. And when everything was rigid, the environment and the robot, in many cases, we could not successfully place the object, even though the perception was fast and we had closed loop operation. If we kept compliance, but we kind of reduced the update rate of control relative to perception, we introduced delay between when we were updating actions, we almost had kind of catastrophic failure in terms of the pipeline. The tight closed loop operation is also very critical to make this work. And when we allowed frequent updates between perception and control, and we kept compliance, but we introduced noise in the output of our tracking system, we also saw the gradual degradation of the performance. So one of the messages here is that actually all of these components, compliance, closed loop operation, and accurate enough perception are needed to make such a system, such an end-to-end manipulation system work. And it also allowed us to go to some a little bit more open world examples, again, kind of packing problems where, this time again, the tolerances are tighter, especially the marker insertion that is shown on the bottom right is a very challenging problem. It is very difficult to do to see, not a lot of point cloud elements on the marker, and again, very tight setup to insert it, or this, plug insertion problem in order to power up, to provide power in the plug, or the cap stacking problem where we have to put a sequence of objects one on top of the other. Now, something that you may complain, yes?
Can I ask a quick question? This is just, I've got to know this. I've been holding my question, but how do you deal with the symmetry around the, like the cylinders and tracking that? Is that just inherent to the, like keeping it, frame to frame consistent or something like that?
Yeah, so have in mind that in the stacking problem, the symmetry doesn't necessarily also harm you from the control side, but you're right on the perception side. It's a challenge as well, and kind of the approach when it has multiple solutions. It also kind of comes up with the one that minimizes unnecessary rotations if the all of them kind of agree in terms of what you see relative to the previous frame. So this ends up and kind of this minimize the rotation relative to the previous frame as long as it agrees. It actually works good enough.
Great. Thanks.
Now, something that also you may complain here is that for all of these objects, we still use models, right? And we have to know the object. We have to have the CAD model beforehand in order to solve these manipulation challenges. And in many application domains, if you go, in the e-commerce domain where you have a company that may be shipping millions of items, can you expect that you will always have access to an accurate model for the object that you're going to be manipulating? And something else that may worry with this pipeline, like the SC3 TrackNet, we're having a network that computes difference for every frame relative to the previous frame. But if you have consistent error in that estimate, will this error accumulate over time and you start not being able to correctly track the pose? At what point perhaps you need to kind of close the loop similar to SLAM and being able to figure out that perhaps, perhaps I should reason about some of the older frames and be able to understand that I have deviated from my estimates. So in the most recent work that we have been doing on post tracking with my former student, Bo and Wen, we focus on the case of tracking without object models, which is a little bit of ill-defined problem of coming up with a pose without having a problem. The idea is that if you have an RGBD sequence, such as what we show here for this manipulated object, but let's say that you do not have access to the model for this mastered model, but you have a mask for that object in the initial frame and you extract a segment from the point cloud corresponding to the object, you want to figure out the relative transforms of this point cloud as the object is being manipulated relative to the original frame. Now, if in the original frame you have a way to figure out the pose of the object relative to the camera, then you would have actually absolute poses for the object in the global coordinate frame. So here we're not going to no object model is harmed during this project. How does this approach work? At a high level, it starts with the same idea that I'm going to be getting, the previous frame and the current frame, and I'm going to try to compute a relative transform. So we are using pre-trained networks for segmenting the scene and figuring out a mask for the object in the previous and the current frame, and pre-trained networks as well to generate key points on the segmented mask. So we have key points about the object's mask in the previous frame and key points in the latest frame. And by doing some matching, we also get features for these key points from pre-trained networks, and doing some outlier rejection, we can get from data association an initial estimate of how the object has moved relative to the previous frame. But now, because we are doing this, without knowledge of models and using pre-trained networks, this is a rather erroneous initial guess about how the object has moved. It's not as accurate as what SA3 TrackNet is generating, because SA3 TrackNet has been trained on the object models and has more information. But this is where we're bridging deep learning that has given us this output and this guess with post-graph optimization, which post-graph optimization has become very popular in mobile robot localization on a kind of closing the loop. But now we're using it in the context of object localization in manipulation. So we are taking this initial estimate, this capital transformation T at the current step, given how we have matched key points for the object's mask relative to the previous frame. And we go into our memory pool and try to see older snapshots of the objects where we may have seen it from similar viewpoints. And we collect a set of key points where we have seen the object in similar views. And we try now to solve an optimization problem. For every pair of snapshot of the object, we impose some constraints. We figure out the key points in the two frames and how they match. We can use the geometry of the object and how it matches between these two key frames. So we build a graph where a vertex corresponds to a view of the object, and an edge specifies constraints for these views, relative transformations of the object from these viewpoints. And we solve this post-graph optimization in a least square sense, and we're getting the best relative transforms between all of these keyframes. This now ends up giving a much more accurate transformation for the latest frame, and it allows us to also go and correct older frames. And if you basically have allowed yourself to rotate an object, you're closing the loop over time, and you can actually correct errors that may be accumulating over time, the same way that you would do in SLAM. If you went back to the original location where you can match features in the environment. And this process can again be executed in parallel with GPUs. This does not run at 90 hertz, it runs at 10 hertz. Still quite fast for a lot of applications, where about a third of the time is spent on the segmentation, a third of the time on feature matching, and a third of the time on the post-graph optimization. And it's remarkably stable in terms of the error. You don't see this increasing error over time in video sequences, again, because we have this ability to close the loop. And although it doesn't use models, it actually behaves even better in some of the popular benchmarks than some of the category level post-tracking methods. I'll show you some qualitative results here in a popular Knox data set. On the bottom left is the ground truth object poses. right next to it, you can see the output of bundle track and how stable the output is and very similar to the ground truth versus both category level and model-free approaches for tracking, where the error very quickly increases and you have these unstable estimates, which really, it's going to kill a manipulation pipeline. In our own data set that we have released for the YCB manipulation of YCB objects inside an effector, again, you can see on the top left, ground truth poses, and the bottom right, you see our solution. You see the solution of TrackNet, which has access to the object model, as well as solutions that have access to the category level or model-free approaches, which very quickly also deviate in their estimates. But bundle track without the need for object models is able to keep tracking the object. And again, we use this approach as in order to unblock ourselves in the context of complete manipulation pipeline. And we try to solve the following problem. Again, it's a kind of a tight insertion and assembly type of challenge. Think of a setup where you want a human worker to demonstrate, only once how to perform a task. Here, we're showing how to insert a gear into a receptacle. And you may have access offline for examples of such gears and corresponding to a category of gears where all of them have an opening in the middle that allows them to be placed. And then you want your robot to execute a similar behavior of inserting this, a new type of gear, perhaps a gear that you have not seen during your offline training. And similarly can be inserted into such a receptacle. And you can see on the top right execution of a robot on a different type of gear. And here we used our tracking solution as a category level object tracking approach. So the pipeline for this solution is quite complex. I want to emphasize that there are kind of three high-level steps. There is an offline representations for how to think about objects in the same category. We refer to that representation as the non-uniform NOx, non-uniform normalized object coordinate space. We do this offline training first, then we see the video that the human demonstrator is performing the task, and then we're performing the online execution. And both during the demonstration video and during the online execution, we're using the bundle track approach that I described before to keep track of where the object is located, both when the human manipulates it and when the robot is moving. But how are you going to be able to follow the trajectory that the human demonstrated into a new type of object from the same category, which object you have not seen before? The idea is that first you're going to reason about how you map point clouds of objects in this category to a pose and a scaling space. So a 9-dimensional space that says, I'm able to go from any object in this category to any other object in this category and figure out that the current view of this object corresponds to a specific 6D pose and a 3-dimensional scaling of that object into a uniform representation for the entire category, which is this NUNOX representation that we refer to. So offline, we train with examples of these gears, let's say, as an object category in simulation, and by taking views in simulation of point cloud of these objects, we're able to map them into a 9-dimensional space representing the pose of the object and its scaling relative to other objects in the same category. And then we have the demonstration with a known shape, and we are able to use the network to map at every point in time during the demonstration video the pose and the scaling of that object relative to the abstract category model. Then we basically are having this ability to get the demonstration trajectory and reason about the trajectory in the abstract space for the object category, and we're trying to transferring it into the new object that we have not seen before. It's not one of our example objects during the training of the representation. And what also became very critical for the transfer of the behavior is that we needed kind of an adaptive dynamic attention mechanism for defining what is the coordinate system of the task that is important for solving this task. Here on the left side, we're using the same representation that we are using in our solution, but we reason about the coordinate system to always be the center of the current object that we're being manipulating, given the point cloud that we are detecting. And if we're always reasoning about this coordinate system being at the center of the object, when the object is different, you may have undesirable collisions, as it is shown here. As we're trying to insert a battery, we have seen a demonstration of a small battery, and we're trying to execute this for a larger battery. And we're trying to match the center of this object to the new object. It ends up colliding with the receptacle. KPAM is an approach, from Rasta Drake's group that operates in the same space of category level manipulation, which requires human annotation of specifying what are the semantically important points that you should map between two objects in order to transfer a specific trajectory from one object instance in the category to another one. But here, the dynamic attention mechanism that we have as part of this solution, it reasons automatically, by thinking, where the contacts arise, how to move the coordinate system, and how I should be mapping what has been seen in the demonstration trajectory into the target trajectory, so that collisions do not arise and I still succeed with my task. And this allows us, for instance, here you see we have done one demonstration of a battery being inserted. And then we're able to transfer it to a variety of different batteries, as it is shown here. All of them follow the same canonical trajectory, and these are different batteries. The same bundle track approach is used to track the trajectory, both in the demonstration and in all of these execution videos. I don't know if you have any questions, and I don't know how much time I have. This kind of covers the kind of efforts that we have been focusing on having fast, high fidelity tracking and reducing the information requirements of the perception approaches, so as to generalize to new object models, and then putting them into complete pipelines where we take the advantage that we have these high frequency perception updates in order to then perform the manipulation planning.
Great. Thank you, Kostas. Very impressive. One thing I want to just keep an eye on the time. It's a little before 5, and I know you were going to talk a little bit about the new work and as well. So, yes.
If we have time, I can try to go a little bit, and it's a switch, a little bit of theme. It's not manipulation. It's still about compliant mechanism, but this time for these tensegrity locomotion platforms.
Okay, I think it's good. We have a good number of people still on. I have to move to a different lab, so I'm going to switch over to my phone if I can, and can continue on that. And then, but I may get broken up, but I'll let others chime in. But we probably could go for another 10 minutes.
Okay, sure.
Okay, great. Thank you so much, Kostas.
Yeah, and the focus of this second, it's a smaller part, is more on the simulation reality gap, and I refer a little bit to simulation reality gap when I talked about synthetic training of perception methods. But here I want to emphasize more on learning controllers for systems with significant dynamics, and we're motivated quite a bit by these tensegrity robots. These are hybrid soft rigid robots like this SuperBot platform that is available at NASA Ames. You can see the SuperBot bot has 6 rigid rods, and it's connected with the 24 cables. The rods have motors inside, and they can pull the cables, and this allows to change the shape of the robot, and it allows it to generate locomotion. So these are exciting platforms to work with. NASA is excited because you can drop them over uneven terrain. They can absorb the impact. They can distribute it over the entire surface of the platform, so they can potentially navigate over uneven terrain. At the same time, they're high degree of freedom systems, highly nonlinear dynamics involved here. Again, very complex to model and have analytical models to work with. So when we started working with them in the beginning, we, I went to my motion planning roots, and I first wanted to show that we can actually generate with sampling-based motion planning, complex behaviors for these platforms in simulation. For instance, I could show that we can come up with controls that deform the shape of this platform to be able to go under a vertical obstacle. And once the platform was able to go under such an obstacle, it could become taller again and navigate towards its goal, or it could go over uneven terrain like the platform shown here. But we could do this work in simulation, and we could generate complex trajectories for these platforms, but we would not move it onto the real system at NASA Ames. Our motion planners kind of needed to have access to the entire state of the system. The sensing available on the real platform corresponds to IMU measurements on the actual rods, and the NASA simulator as well that we were using, had a gap relative to the real system, so this made the transfer quite difficult. At the same time, Sergey Levin and Peter Abil were also working towards applying, one of their reinforcement learning frameworks on the tensecurity platform. So they actually applied a guided policy search on a tensecurity robot, and the team was able to demonstrate that they could actually make one such robot at least learn with reinforcement learning these rolling wheel gates. So the tensecurity can move forward on a straight line. And we got excited, and we tried to use guided policy search to start learning more complex behavior. But we started facing the kind of high data requirements of the RL approach in order to be able to learn more complex behaviors. For instance, we tried to use the same learned policy to move not on a straight line, but we were trying to hit waypoints on a curved trajectory, and this was facing a lot of challenges. So we looked into how to improve the data efficiency of the reinforcement learning strategy in order to learn more complex behavior. Something that we took advantage of is that we could actually generate in simulation a lot of these complex behaviors using our kinodynamic planners, and we were able to bootstrap the RL with complex strategies that were valid in simulation. There was a gap between simulation and reality, but now the RL had seen more a complex sequence of controls, and that was now, and the RL knew how to map the sensing input that was available on the real platform to these complex behaviors. And we also reasoned about the symmetry of the platform. This Super Robot is highly symmetric. Instead of reasoning about the global pose of the system, we reasoned about its support triangle and being able to move the center of mass over neighboring support triangles, which actually decreased quite a bit as well the data requirements. So we had now this RL approach that was much more data efficient. It allowed us to able to train locomotion gates for navigating over uneven terrain, as we show in this simulation setup here. And I just want to emphasize that what the controller receives as input corresponds to the actual inputs that the real robot has available. Also, the cable rest lengths can be measured, the bar rotation rates, and we also can measure the angle of direction of motion and the angle of direction to a specific waypoint. So this is input, and the output is 24 controls corresponding to the lengths of the cables, and each cable connects to end caps of the rigid rods. So we could now generate this very complex behavior in simulation, including for uneven terrain. But were we able to transfer this onto the real system? So my postdoc at the time, David Surovic, he went in simulation and generated a very harsh environment. We knew that our NASA collaborators were interested in achieving an uphill motion for their platform. So he went and generated this 25 slope, very harsh simulated terrain, and learned in simulation this controller that was able to go uphill in this very harsh simulated environment. And this controller now was able to work actually on the real system in a little bit less harsh environment, specifically for a 50 degrees slope on the real environment, and much flatter actually uphill environment. But you see actually the same controller that David trained in New Jersey. We just shipped it to California at NASA Ames, and our collaborators Jonathan Bruce and Massimo Vespignani there, they run the same controller on the real platform, and it was the first time that they were able actually with that hardware to demonstrate that they could go uphill. And you see how much the controller actually makes the platform have be almost horizontal and have very low center of mass in order to be able to go uphill. So it was a success that we were able to come up with a gate that was now executable on the Super Bowl bot, but it still took quite a bit of tuning to be able to transfer this solution from simulation to the real platform. And this motivated us to actually get into differentiable engines for these very exciting but complex robotic systems, where we could train a simulator just by seeing a few examples of trajectories of the real system, so that then we can use the trained simulator to train policies and then transfer them back to the real system. Now, a lot of the work on differentiable engines, they view the differentiable engine as a large network which receives the current state of the system, the control, and gives you the next state. And then if you have as a label the state of the ground truth next state of the system for the real robot, given the same input, control, and state, then you could compute the loss and train your neural network. Here we tried to build a much more explainable physics engine, looking a little bit more similar to some of the traditional physics engine, where each one of the components, however, is still differentiable, and we could use gradients from the loss in order to train them. The fact that the tensegrities, their soft elements are also single dimensional, one-dimensional, and those cables tend to always be in tension. Also helps to introduce some linear models here for some of the physical parameters, and to try to learn an explainable set of parameters from the real data, right? So the input here is a trajectory of the real robot, and you try to match it in your physics engine so that the engine closes the gap with reality. One of the challenges that we face as we started, we first tried to do this work in a sim-to-sim evaluation. So we used a model of a tensegrity in MuJoCo as our ground truth system, and then we were trying to train the differentiable engine to match the output of MuJoCo, and started moving incrementally towards more realistic setup, where we would use sensing information to detect where the robot is in the real world, and then train our differentiable engine. One of the challenges is that you have to run your differentiable engine at very high frequency in order to make accurate estimates about what happens at contact points. So we're actually running the differentiable engine, close to, with hundreds or sometimes even thousands of hertz frequency, so as to figure out when the contacts arise, and that's when forces are computed. But if you're going to be getting a real robot trajectory and you're tracking it, you're going to be getting a much lower frequency of observations, perhaps at 30 hertz, whatever your sensor may be running at. So your samples of where the real robot has been may not actually contain the points where the actual contacts happen, and where the interesting physics took place. So there is this mismatch between observations for the real robot and what the simulation frequency is running, which also required kind of an incremental a process where we had to make a lot of predictions with our differentiable physics engine and train the engine in a recursive pipeline where we get very infrequent losses from our ground truth observation of the system. So we also split up the training process. So we first focused on identifying non-contact parameters. So we gave example trajectories first of the platform where we moved it without any context. You know, we were shaking the tensegrity so as to see information about the cable responses, and then we saw trajectories where the platform was executing locomotion gates, and then we identified also these contact parameters. We were able then to learn locomotion policies and execute them back to the ground truth system. So here, this is a sim-to-sim evaluation. On the left side, you see a policy that has been trained on the ground truth Mujoko system. The policy took 100,000 data points to be trained. So these are state, control, next state data points. So we required 100,000 data points for the left policy. The right policy is actually trained in the differentiable engine, which required only 1,000 ground truth data points to be trained. And then it was trained in that engine and was transferred back to Mujoko, and was very similar to the original policy. So with 1% of the data requirements in terms of the ground truth system experimentation, we were able to train a policy that was very similar as the one trained directly on Mujoko. And eventually we got into a real system and performing a real to Sim2Real transfer. The actual platform that we have been using the last year is a platform at the Rebecca Kramer Botilius group at the mechanical engineering department at Yale. You see here, we're using an RGBD sensor that is placed externally to track trajectories of the ground truth platform. So we run initially random policies with the platform to be able to observe it. We run a pose estimation solution to reconstruct where the robot is located. And you see here at the bottom video our reconstruction of the pose estimation. Right. So this robot has 3 bars. So each bar has its position and orientation. So this is an 18-dimensional space that we are tracking. So the real to Sim2Real pipeline here is, you know, execute this random policy on the tensegrity robot, observe the robot and perform state estimation using the RGBD data. Use these low frequency observation from the camera to train your high frequency differentiable engine. And then for this physics engine, learn a policy that you then execute on the robot. Now, the first time that you learn a policy in the engine, there is going to be some gap between the policy executed on the real robot and the simulation. But then by re-observing what the robot executed around this policy, we can go back to the simulation, and now our simulation is tuned again and becomes much more accurate in predicting the outcomes of the real system in the vicinity of that policy. And we bridge quite a bit the gap. On the video on the bottom right, you see the execution of some different types of policies, either straight line trajectories or curved trajectories executed on the real robot and then identified on the simulator. Interestingly, we're actually able to match very well the poses of the real robot and of the simulator, but we cannot match the duration of the trajectory in simulation yet as accurately in terms of what happens in the real world. But this has been our first success in terms of observing a system in the real world and as complex system as, you know, such a tensegrity robot that is both rigid and soft, and then go into simulation and tune it good enough that then a policy trained in this simulation qualitatively is very similar in the real world and in the simulation environment. So some of the takeaway messages for what I mentioned here. I'm a big fan of compliance and the progress that our mechanical engineers and robotics are doing with bringing adaptive robot mechanisms in helping us to deal inherently with noise and uncertainty. But from the AI side, we also need to be tightly integrating perception and planning tools. I believe moving from a kind of snapshot-based perception solutions to continuous streaming of representations that are useful for manipulation is very critical. We have shown here that vision is already powerful enough, but integration of vision with tactile information can also significantly boost the capabilities of manipulation systems. We also need robust motion primitives that are built so as to deal with failure modes, and big supporters of using data-driven methods, especially for these emerging family of soft robots where accurate models are not available. But at the same time, that's a domain where we need to deal with the Sim2Real gap, but in a way that helps us to generalize across problems and setups. Thank you for those that stayed around. I know we ran a little bit longer, but thank you for those who were able to stay longer and listen.
Thank you, Kostas.